So the finite state machine for the controller that we discussed previously did not tell me anything about how or what is happening on the serial data line, or actually the serial clock. So let's see how we actually control the serial data here. Because we are utilizing the open drain technology, so where the data line is actually connected through a pull-up resistor all the way to the power or the positive power, there's a little bit of a specialized output control logic in here. So the finite state machine that we covered is here. It actually gives me a few signals. So from these signals, I can actually figure out the command. I can figure out whether I'm actually reading or writing, whether I'm in a data stage or non-data stage. Maybe I'm on a start command or a stop command or something like that, or a stop condition. And we will have this output control logic. So let's see what this output control logic actually does. It's actually a very simple it's a very simple combinational circuit in here. So let me just explain how the system works using an example because it's the simplest. I'm gonna start by a right condition. So the system, you can think about it in conceptually. It has a couple of registers in here, one for the receiving end or RX, and then the other one is for the transmit. Each one of them here, just to remember, is actually 9 exact bits. And the reason why we use 9 bits is because we need 8 bits for the data and we need 1 for the acknowledged bits, whether you're sending or receiving. Okay, we have here is what we call a tri-state buffer. This is only asserted if you put a 1, you basically connect. If you put a 0, you do not connect. And this is basically because you're using open drain technology and whatnot. It's like all of this, basically the data line goes directly in here. So this particular output control logic controls what happens with this buffer. So let's assume that we are writing. So if you are writing, that means you are sending data out. So what you do, effectively, you basically say, okay, 1, 0, 1, 1. Let's assume that this is what I want to send. And because it's 9-bit, I'm going to have to say, let's assume another couple ones and a couple of zeros. Okay, these are the 8 bits that I want to send. Another bit that you should be sending, or actually I don't care about sending it, it's actually, I'm going to call it as an X. It's actually the least significant bits, which is basically the acknowledge, because you should not be sending an acknowledge, you should be receiving an acknowledge. Okay, so what happens in here? Well, as it turns out, that this particular output control logic knows that I want to send, and the reason why it knows that it wants to send is because the command tells me I'm writing, okay, and the finite state machine tells me that I am within the data, okay, so because I am within the data, I'm just going to basically activate this, and I'm just going to put a 1 in here. And because I'm putting a 1 in here, that means the data actually gets transferred one at a time. So the first clock cycle, what happens is you take this particular 1 in here, the most significant one. Let me just do this. The most significant bit, you put it in here, you put it in here. Now it passes to the bus, it goes on the SDA, and it goes to the slave. Also at the same time, because the way that the receiving shift register is actually happening, it actually also receives it. And as it turns out, that both of these shift registers, whenever you're shifting, they're shifting at the same time together. So any shift operations happens together. Of course, I don't care about receiving the one because I'm sending it myself, so I have it, but this is how this operates. And you do this one bit at a time. For example, the next one would be the 0. You go in here, you send it to the slave, and at the same time, you actually store it in here. And you go all the way through till the very, very, very end in here, okay? So at the very end, basically, you move the 8 bits, and now you have the 9-bit in here, which is X. So the 9-bit in here, which is X, I can tell from the finite state machine that this is basically the acknowledge bit. You should not be sending the acknowledge bit. So what we do is that particular output control logic in here, the way it's written, it's going to tell me, okay, just put a 0 in here. By putting a 0, you're effectively just basically disconnecting that shift register from the data line, and you're releasing the data line. By releasing the data line, now the slave has control over it, and the slave can actually assert that signal. And generally speaking, you assert it by putting a 0. And the reason why we choose 0 for asserting is by default, that SDA, if you don't put anything on it, it's actually connected through a pull-up resistor to a 1. So put a 0. So if it was a 0, you will see that basically that 0 comes in here. Okay, the slave sends that 0, you move it in here. Of course, it doesn't move back in here. It just moves to the receiving end of the register, and that's it. What happens as well is whatever you put here, and whether it's a 0 or 1, it's dummy, it gets shifted out. But because it gets shifted out to a buffer that is not connected, it's basically you threw it out. Basically, it doesn't matter. It's dummy. What matters to me is the following: that the slave has received it, and now I can read my shift register least significant bit in here, and I will know whether that particular slave actually asserted it or acknowledged it or not. The receiving is very, very similar. So let's assume that you want to receive some sort of data bytes coming from the slave. So what you do is, let's assume that the slave wants to send me 1111 and 0000, okay? And of course the slave doesn't send me an acknowledge. So what happened is this will stay at 0. This one here will stay at 0 for the first 8 bits, okay? So, and what happens with during these first 8 bits, you're sending the 1, blah, 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 and then your receiver actually gets that. Again, the same thing is happening in here. Those shifts are actually happening exactly in here, the same exact shifts, but I don't care what data you have in it. Generally speaking, you loaded with a bunch of X's in here, okay? X, 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 X. What X stands for 0 or 1, I don't care about it. Okay, what matters to me is the following, is that whenever you loaded that particular register with a bunches of X, 1, 2, 3, 4, 1, 2, 3, 4, you also loaded it with a 0. And that 0 indicates to the slave that you can send it to the slave, and that's what happened. So the output control register in here knows that it's actually an acknowledged bit and knows that it's actually a read signal because it actually needs that. So what it happens is actually it does the following. It says, okay, I do not need to release that anymore. This should be a 1. Okay, and now I can send a 0, which is an acknowledge to the slave, or I also can send a 1 if I want to, basically, if it's at the very, very end and I want to stop the slave from sending me any data. So you send it to the slave, and at the same time you actually receive it. So when you take a look at the receiving here, the receiving shift register, you basically received a new data point, a new byte, and you also received your own acknowledgement, which is dummy and I don't care about it. But what matters now is that I was able to receive that. So this is how we do that, and this is how the output control logic. So when we take a look at the HDL, you'll see that it's actually the output control logic will do the same. This is exactly what's it doing in here.